Up to this point, we have not yet discussed how we will go from our observations and our data to building a model. We have not yet discussed that process because there are a lot of different directions that we will go, and we'll want to spend a lot of time on it. What I can tell you about that process is that that's going to be a process of looking at our observations and knowing what our error measure is and building the best model that we can with respect to the known error measure and the type of model we want to build. However, it's very important to never lose sight of our goal, which is to take these various models and use them to predict what the outcome would be once the system encounters novel data or data that was never used at all in the building process. So let's imagine if you need an example that we have some data that we want to fit a model to, and there are different types of models that we could build. For example, perhaps a linear model, a quadratic model, and an exponential model. And individually, you should suppose that these models have been built to optimize the RSS error measure or any other error measure that we'll have introduced to this point. If each one of the individual models is entirely optimal with respect to the data from which it is built, how will we be able to compare these models for how well they perform on unseen data? So here I'd like to talk about our general strategy for how we're going to approach that in data science moving forward. To begin, our philosophy is as follows. Instead of using all of the observations that we have to build our models, let's split our data. Now, when you have a good amount of data or you're just getting started in data science, a roughly 80 to 20 split in your data is going to be good enough. Of course, there are circumstances where you may want to split your observations up differently. But again, for a starting out example, let's assume we make an 80 to 20 split, where roughly 80% of our data is going to be what's called training data. And that's the data that we're going to use to build those various models. If you're keeping up with the example, the linear model, the quadratic model, the exponential model. The remaining totally independent 20% of our observational data, we're going to keep completely blind from the part of the process that builds the model. So none of this test data will be touched at all when we create those three models, linear, quadratic, exponential. What we're then going to use that test data for, since we won't be using it to build our models, is instead of running the residual sum of squares on the data that was used to create the models, we're going to run our error measure, here our residual sum of squares, on the test data. Running your error measure on your test data and seeing how small your error measure is on your test data is a much better proxy for how that model will do on novel data. To bring this back to reality, when we have all the information that we could possibly want in front of us, it's much more straightforward to create a good model of that situation. And therefore, it should be relatively easy to build a model that has a very small error on what it was built on. In other words, when you have all the information you could possibly want, it's pretty easy to model it well. But that's not the goal. The goal is to make a model that will fit new data well. And that's where the test data comes in. A much better way to see how a model will fare on novel data is to run it on a different sort of practice set, which is our test data. Here, with our test data, we have knowledge of actual input and actual output, and we can also apply the model to the test data to get predicted output. That allows us to imitate how a model built on almost everything that we observed fares on some new to the model data where we actually know the outputs. And that gives us a much better predictor of how these models will do on new data. And so it's the RSS value on the test data that becomes incredibly important when we assess a model's accuracy to see how it will fare on totally new inputs for which we won't have those actual outputs to compare with our model's predictions.